Okay, welcome everyone to the INQA seminar this week. It's my great pleasure to introduce Michael Huang from the University of Rochester. And although this is the International Network on Quantum Annealing, I guess it's very important for people in quantum annealing to keep up with classical competition of various forms. And I think in particular, novel forms which relate closely to the Ising model. So Michael's talk is on a Dynamical-System Computing Platform with a case study on BRIM. Michael, over to you.
All right, thank you. Thanks for the opportunity. So I'm going to start with sort of the general vision behind our work. On the right-hand side, we're showing a chip diagram of today's edge device. It's already, this thing used to be called a CPU. I'm a computer architect. That's what I do for a living, try to design these systems so that they're more energy efficient and faster in performance. But today they're already very diverse with fast CPUs, efficient ones, GPUs, MPUs. I'm going to predict by mid-century, we're going to see special dynamical system units to help accelerate certain workload. And on the left-hand side, in the data center supercomputer domain, we're going to see special purpose computers. And I dare predict that we might outnumber at least circuit model quantum computers. So this is just, the dynamical system unit is a name that I coined. I'm not terribly happy with it, but we'll go with it for the moment. But many of you know that NP-complete problem can be mapped to the Ising formula. I'm a minority here, Ising, but coming from Germany. His name is actually Ernst Ising. But anyways, this is why a lot of people are working on various Ising machines with all sorts of fancy physics. But I'm a computer architect, so from a user's perspective, we need the machine to be useful at the end of the day, regardless of the implementation. So you may have physical entities to represent spin. That's really the first step. You need to make them programmable in strengths. That's adjusting these blue values. And these are really basic steps. From then on, you need to show me, user, that you can arrive at good quality solutions. So that means low energy solution, preferably the ground state. You better convince me that there is some fundamental reason this is happening, so the invisible hand of nature, and demonstrate empirically that you can solve problems. So again, from a user's perspective, at the end of the day, you have to do so at competitive cost and both execution time, the energy spent, and the construction costs. Users are very demanding today. So in this talk, I'm going to try to make a case for this CMOS-based dynamical system. I would want to convey the idea that it is a very promising computational modality. So I'm going to briefly talk about this machine. So it's what we call BRIM, and it's leveraging the versatility of CMOS platform today, and it's going to allow us to do a number of things. I hope to give you 3 examples if I have time. So let's start with the system. Again, we don't need very complicated physics. A capacitor is a very good approximation device to represent spin, right? If I have the top device having a higher voltage, that's spin up, otherwise it's spin down, and I can connect them either top plate to top plate, that would be a parallel connection, indicate positive correlation or positive coupling, and anti-parallel for negative coupling, and higher resistance would be low coupling or low strength coupling. So in fact, if you take the JAJ that we're familiar with, the 1 over that should be the programmed resistance value. So here's a very quick example to show you a graph, a max cut graph, where the WIJs or the weight, if you turn that, put a negative sign, that would be your JIJ. You program it, the left-hand side is exactly what the graph indicates. Suppose I start with some random initial position, and it will end up exactly max cutting this particular graph. So this is a contrived example. You can work through this yourself. But the general idea is, in this particular case, it kind of worked. It's a contrived example, I admit, and there are real-world problems, such as what if my graph has a frustration? What if the capacitors leak? So there's lots of things that you need to do to make the system work. One of them is to keep the nodes bistable, and hence we call this kind of machine bistable resistively coupled Ising machine, or BRIM for short. So the overall system is a bit more complicated than the setup. You have your nodes, perhaps to read out, you have some DFF for that. You obviously would need annealing control to do spin flipping so that you can escape local minimum. But you have the matrix and array of digital to analog converters so that to program these couplers, because that's what the coupling values are coming from. So anyway, at the very beginning, we had a system that we call ZIV dialo. This is really because this IV curve shows a slanted Z shape. So the idea is when the value is positive, we push the value towards positive rail, the negative rail to keep them bistable. And then it turns out we don't really need that. So in terms of the invisible hand of nature, you can kind of work through, this is just the governing equation of the dynamical system. If you work through that, this is really a simple, linear, high-dimensional dynamical system. And in fact, it's a gradient system. So you can work out the potential function. It looks exactly like the Ising formula. So you show that this is a proper Ising machine physically, and you can start by setting it up, give it an initial condition, do some annealing schedule, injecting a lot of spin flip at the beginning, gradually reducing the strength of that injection, and at the end, latch the result, and that's your annealing process. So how does that work in reality? Well, we don't have a chip at the moment. I'm working with chip designers in my department to try to fabricate the first one. But here I'm going to show you some numerical simulations. This is behavior model. Luckily, if I can put this away, good. Luckily, a lot of work out there use GSet. So we use that. This is really just a set of graphs with variable weight, edge weights. The whole set has up to 20,000 nodes, but we use smaller ones because simulation is painfully slow. And to compare to certain machines like D-Wave, we have to use smaller graphs. So we use the same generator that generate the regular GSet to generate small graphs, and even something very tiny we can enumerate to see where the ground state really is. Oh. So I hope the screen is showing fine. So this is an imperfect comparison. I have to apologize because it's various machines, CIM, coherent Ising machine, we don't have access to that, but they did report on certain workloads. We're going to compare to that. D-Wave is an actual physical, it's a commodity machine if you wish, while BRIM has not been prototyped. So it's an unfair comparison in that sense. So there's a whole bunch of methodological constraint, fixed data point for CIM, fixed annealing time, at least for the budget that we had. This is really a high-level coarse grain comparison. And in the case of D-Wave, you probably know, to get a map, to get a graph to map on the machine, you have to go through this minor embedding process. And this is a graph showing as the size of the graph that you're dealing with increases, the number of physical nodes increases a lot. For the case of Chimera graph, that's the yellow dot, the most we can do is 126 node graph. This is a GSet, small GSet graph. The machine that we had access to happened to be 2000Q. This was a couple of years ago. Now there's a 5,000 node machine out there, but we haven't redone these experiments. And also, you probably, if you've tried this, the time it takes to embed the graph is horrendously long. In fact, much longer than the time it takes to solve the problem using simulated annealing on a laptop computer. None of that is included. So we're only comparing annealing time in this case. So maybe we'll start with CIM with this kind of regular size graph. Instead of showing the absolute solution, we measure the solution quality to that of the best known solution anywhere. So the smaller, the better for this distance. So 46, 47 was what they reported. And so to match the same solution quality, we see that we can be quite a bit faster, coming down to smaller graphs. D-Wave for that time, we had 20 microsecond annealing time in both tiny and small. We can get to ground state in our runs. This, by the way, is all, I think, 20 instances per problem.
I haven't understood what the 46 and the 47 means. I know what the...
Sorry, yes. So treat this as a max cut problem. You will get a max cut value and compare this to the best known solution. So 46 is just not quite there, right? So the smaller the distance, the better.
Got it. Thanks.
For these tiny graphs and small graphs, we couldn't get to ground state. By the way, this is best solution out of 20 runs. But for BRIM, we can easily go to ground state for these. And for the tiny graph, we can verify that that indeed is the ground state. So perhaps this kind of shows you a general idea. This, I forgot exactly what this is, G22 perhaps. The x-axis is time and log scale. Y-axis is max cut. The higher, the better. The target is the best known solution for this particular graph with a particular value. And so what we run is we take different annealing time and run them and measure, again, best out of 20 runs. And so this curve shows simulated annealing on a desktop machine. This is kind of BRIM simulation. These two are what we call accelerated simulated annealing, which is basically some digital circuit that you can think of as a hardwired machine for simulated annealing, but they have some architectural solution decisions that made it very specific to, for instance, they're doing near neighbor graphs. You cannot map a general problem. And so we idealize that. We have a model. So the the red one is probably an upper bound that you can probably not achieve. This purple one is sort of what they reported as a result for a particular size. So the comparison here is we think we can be, orders of magnitude better than von Neumann machine, a general purpose machine. So the takeaway from this particular study is resistively coupled electronic Ising machine is a very promising design among all these machines out there. We know that auto connectivity is very important because you want to map a general purpose problem. That's what user gives you have no control. It's very easily achieved in BRIM, although you have to pay O(n) square cost to create all the couplers. And there are some key challenges for us, and I would argue, in fact, for all Ising machines. So what if the problem is bigger than the hardware? What if you have high order problems? We all know this paper, it's always here on my desk, right, that we cite all the time, Ising formulation for many MP problems. But in fact, many formulations are higher order. They're not QUBO, they're not quadratic. And so when you do convert, you will see that you need a lot of auxiliary spins that hurt not only the spin, the speed, but also the solution quality. And also we want to go beyond combinatorial problems. So in this case, CMOS compatibility, I believe, is a key contributor to allow us to tackle this. So I'm going to show you 3 examples very quickly if I have the time. So the first scalability problem. So let's start with the problem. X-axis is the size of the graph. Y-axis is the speed up. And I'm pretending my hardware has only 500 nodes. And we can see as the problem gets bigger and bigger, I'm using more and more the hardware, the speed up goes up. That's a good thing. And then boom, when it hits the threshold, I'm starting to solve a bigger problem. What do? Currently, in the red line, I'm using D-Wave's open source solver, which means I do some decomposition, put some hardware, use the hardware to solve a smaller problem and combine the result and all of that. You see a sharp drop-off. To show you more clearly, this is zooming in. The x-axis is only from 500 to 520 node. You see the drop-off is very significant. This is assuming, this is a simulation result, assuming the hardware is our hardware, BRIM. So the first thought, maybe the hardware, the software is a little bit unoptimized. So we did try to optimize that. That did buy us about an order of magnitude or even more. But still, in this graph, you can see the sharp drop-off. It turns out this is not even a coincidence. There's a fundamental reason. We think we take some we take some workload, put it on a hardware Ising machine. The rest is conventional computing. Very quickly, the conventional computing portion is starting to overwhelm and dominate the total cost. This is at the moment quite fundamental. So if you want to do this divide and conquer, kind of map some workload on the CPU to help, and this is the slowdown that you have to suffer. It's a classic Amdahl's law bottleneck. So a quick solution would be, conceptually, if I put multiple chips, hook them together, if I have an n node chip, I have k square of them, put them together, it's just a kn spin. It's a machine that is k times larger in the number of spins. And of course, k squared times more critical resource, which is the coupler. But in reality, the communication of analog values is just not going to work. So you have to do something to the architecture. And this is what we did. You use digital interface rather than analog interface. You transfer spin state rather than current measurement. You do a whole bunch of things. I won't bore you with the detail. That's all in the paper. But still, at this point, if you're talking about multiple chips talking to each other, the communication bandwidth is the limit. To fully utilize the speed of the hardware, you need about 50 terabytes of, per second communication. If your communication is 10 times less, then you have to slow down your system dynamic because that's what you can support. So again, we did a whole bunch of things. Don't know how much time I have. I'm going to just skip the detail. The point is, you can play tricks. These are the tricks that we as architects play all the time to improve performance of uniprocessor or CPUs, GPUs, and whatnot. So we play these tricks, and in the end, we can kind of match the inherent speed. So this is perhaps one K2000 simulation. This is, again, a standard graph that people use. The fastest machine out there, this is simulated annealing. Again, 20 runs per annealing time per experiment. So the shaded area shows you the 20 run in terms of max cut. The higher, the better. The dotted line is the best known solution for K2000 in literature. Simulated annealing at the far end. The best other state-of-the-art solution is this thing called simulated bifurcation machine. I believe they are on Amazon, so we can run them, but this is, we just take their word for it. So this is one version. They have multiple versions. They reported 2 annealing time result, 20, I think they did 20 runs, I could be wrong. So about a few orders of magnitude compared to simulated annealing, or an order of magnitude on a problem about 2000 spins. And if we try to make a bigger problem, in this case, because they tried K16K, so we assumed a multiprocessor chip, that's what M stands for, 4 chips each, half of the number of nodes. And then we get this graph, which looks a little busy. These are all our multiprocessor architecture, depends a whole bunch of things. What is your communication bandwidth? Low bandwidth obviously gives you the worst performance. High bandwidth, better. 3D integration, which is particularly helpful for stacking a bunch of machines on top of each other in a 3D integrated chip that will give you tremendous bandwidth through this thing called TSV, or through silicon via. And that will allow you to fully leverage the speed of the dynamics. So with that, at this stage, you can beat SPM by more than 2 orders of magnitude. So the point is, with CMOS, we can actually build this support element for the machine to perform on a bigger problem. So let me turn to the second issue. The challenge is, let's take satisfiability as the problem. Technically, it's a COP, it's a combinatorial optimization problem. But this particular one has 3 challenges beyond, let's say, we're trying to solve a max cut problem. First, when you convert, this is a CNF form of a 3-SAT problem. And the way you convert that to a Hamiltonian is just this formula. Here's a quick example. You can see this, by the way, it's a QUBO formulation. I'm not using Ising formulation. QUBO formulation is better for SAT, less awkward. You can clearly tell that there are 3rd-order terms. And in fact, there are so many 3rd-order terms that is a problematic issue. So that's problem number 1. We have 3rd-order terms. Second, by its nature, satisfiability requires reaching ground state, right? When this Hamiltonian reaches 0, which is its global minimum, you get the solution. Otherwise, you don't know if it is SAT or not. And finally, and here's an example to show that when we're doing this optimization, we're just trying to get to some good solution. And this is, by the way, just known best solution. Not even, you can call it presumed ground state. We don't even know if it is the ground state. Nobody knows. The third challenge is really simulated annealing is probably a very good, this is the Isakov version, the best we can find. We even optimize that one. But this, there's not a whole lot of improvement over this type of algorithm out there. But in terms of SAT, there's a dedicated community of people. Every year they have new competition, a new winner. And this is comparing two systems from 8 years apart. X-axis is time, y-axis is the cumulative number of instances that you solved from the benchmark suite. No matter which way you cut it, the newer version is far superior than the older one. So the compound rate is about 15% per year. So if you think about that, that's about 3 orders of magnitude in 5 decades. And so the SAT community has been there for this conference particular, probably been there for 20 plus years. So you can clearly see, imagine this state-of-the-art curve moving steadily to the left as time goes by. So that really compresses our space, right? So we know that QUBO can be converted to quadratic form. There's various flavor, Rosenberg, KZFD, that's the author's name. But let's just take a look how bad the result is. The x-axis is variable size. This is SAT variable. Y-axis is time to solution. This is with 99% probability, the time it takes to solve the problem with a 99% probability. The red one is KSAT. The purple one is simulated annealing, what we call SAC, solving the cubic objective function. And the other two are the two quadratizations. You can see that simulated annealing was a pretty good solution, but as the problem scales, even just these are tiny problems, it's already worse, and the quadratization worse still. And if you compare D-wave, which is this blue line over here, and the scaling trend is quite correlated or well explained by the green line, which is cubic quadratization, of the objective function plus embedding. So that explains why this is very poor. So the point is, if we rely purely on quadratization, I don't think we as a community, all the physical Ising machines out there, have a chance to compare, to compete with conventional machines. So, but with CMOS, we can actually do a lot of things. One thing we can do is to add a cubic interaction. That's not difficult at all. You just need multiplication of 2 spins. And in fact, because you're only treating them as spins, an AND gate is a perfectly okay multiplier to use. So we added the third order term, and that blew up the system size quite a bit, but it got better. But then we're still not competitive with respect to a conventional machine. And that's because what I call the navigational efficiency. Traditional algorithms are just so good from the beginning initial condition to the final solution. They need to visit fewer numbers of phase points than we need with a pure cubic term random annealing. So we tried, took us a lot of time. We added a heuristic, the details is here in the paper if you want to read. With this heuristic, and it's quite easy to generate, again, thanks to the CMOS platform. So we were able to cut the gap by quite a bit so that we're finally competitive because our machine is very quick. If you think about it, our machine, there's no exponential speed up, no entanglement, anything like that, right? It's just a fast dynamics. For the time it takes for simulated annealing to visit, I don't know, 1 phase point, we can visit 10 to the 5 phase point. And so in the case of simulated annealing, comparing to simulated annealing, solving a max cut problem, it turns out we need to visit about similar number of phase point to reach the same solution quality. But here, it's a very different story. X-axis shows the number of flips or the number of phase points you have to visit. Y-axis, this is cumulative distribution. So you have believe this is 40 problems. I could be wrong on that. And you're just solving each problem and see how many bit flips you need or how many phase points you need to visit. So towards the left is better, towards the right, that's inefficient. So this is after our optimization, the details over here. We call this whole thing AIMS, just to compare, which stands for Augmented Ising Machine for SAT problem. So you can still see conventional algorithms. These are CPU algorithms, walk-SAT, prob-SAT. They are about order of magnitude, at least at the median point compared to our algorithm. So they are very, very efficient. Is the story. So anyway, this, at least with the help of the new circuit that we introduced, we are finally competitive in terms of time. That's because our dynamic is faster, even though we need to visit far more phase points to find the solution. Finally, we want to go beyond COP. And so for this case, we obviously chose what's called energy-based models. They have energy in their name. These are machine learning algorithms that are really amenable to acceleration. The conventional training of the so-called RBM, restricted Boltzmann machine, it's called CDK, CD standing for contrastive divergence algorithm. It's a form of a stochastic gradient descent. So if you look at the math, it boils down, the training boils down to this formula, and the angled bracket means expectation. The expectation cannot be calculated in closed form, so you do sampling. And this is where dynamic system or Ising machines shine, because as the system evolves naturally, we can just take samples. And in theory, they are just as good samples as the conventional algorithm did setting up a Markov chain or Gibbs sampling. So anyway, long story short, we added some support to make this happen because we need to accumulate stuff. And it turns out you can accumulate charge as an proxy for accumulate weight change. So it's a fairly straightforward application. And a machine like that can actually absorb all the functionality of the algorithm, and the machine can really just, you play a movie essentially on one side with the training samples going in, and the machine will just learn. There is some nonlinearities. We actually simulated quite a bit of mismatch, noise, and all sorts of nonlinearity, and it turns out to be quite robust. And this is understandable. This is a machine learning algorithm. There's lots of robustness in kind of handling variation and noise. In fact, the entire algorithm is stochastic. And one can make the argument the conventional approximation of that is an even worse approximation than what the hardware's variability brings you. So this is a very interesting kind of application. It really makes the hardware's property shine. And this is why in the end, we show that the energy efficiency can be 3 orders of magnitude. This is not comparing to CPU, but comparing to an ultra-efficient platform that is intended to accelerate machine learning algorithms, and that's TPU. So anyway, I hope that I gave you a little bit of a picture of what we're doing. We show that simple circuit can already help you build very effective dynamical systems. These are transistors optimized for von Neumann computing, but the same optimization allow you to build very fast and energy efficient dynamical systems. So instead of leveraging nature-inspired algorithms, you kind of create nature-based solutions to directly embody those algorithms. And the CMOS technology is also helpful in a number of ways that I showed. Helps you to get peripheral support so you can be scalable, or at least more scalable. Can help you improve a certain type of COP, such as SAT, and expand target problems into machine learning algorithms. So we're very excited to work on this. We have our work cut out for us. We understand that kind of in both ways of the meaning. We know exactly what needs to be solved, and we also know that's not easy at all. We expect many challenges so far. For the machine to be really useful in the future, it has to have a relatively broad domain of applications. So far, everything that we've done is very application specific. So we don't have a unified architecture yet to support a whole range of applications. We have yet to deliver the first prototypes, so some of the comparisons is unfair in that sense. We don't know how bad the first chip or future chips will perform and what countermeasures need to be deployed on these chips. So whether these non-idealities will hurt us, we don't know. That's partly what's exciting. So thank you. I'm happy to take questions.
Good, thank you very much, Michael. It's a very interesting presentation. Round of applause on behalf of the audience from me. And as Michael says, if there are any questions, I'm sure he'll be happy to answer them. Maybe I'll start with a question. I can't recall whether I saw any scaling of performance metrics with respect to the system size for your CMOS-based approach.
Good. So perhaps this is the best kind of proxy for what your. So if you think about the dynamics, the more spins you have on a chip, the better the system, because it's acting in parallel, as opposed to, let's say, simulated annealing. So to a first approximation, the bigger the chip, the more and the same speed, the same operating speed.
This speed up is the ratio of the performance of your system and the D-Wave with respect to simulated annealing. Have I understood that correctly?
Yes.
Okay. So I guess then my next question is, I mean, simulated annealing, I'm used to thinking in terms of, number of iterations or number of steps.
Yeah.
And a D-Wave, I'm used to thinking in terms of annealing time. So, so how are you doing that ratio here?
So the way I like to think about this is that in simulated annealing, at the end of the day, if you ignore the rejected moves, you're moving from one phase point to another phase point. So yes, you have in the version that we're having, the loop is based on what's called sweep. This is Ising version, right? But at the end of the day, how many phase points you visited. So as I mentioned, that we seem to find a pretty good agreement that every time to get to the same solution, starting from random initial condition, we appear to be in the same order of magnitude in terms of the number of spin flips that our dynamical system goes through. So we don't know why there's a fundamental reason for that, but empirically that seems to be true. I'm not talking about exact agreement, but reasonable agreement within an order of magnitude, 2x within each other in a wide range of application, wide range of the same type, you can argue, G-set type of problems.
But again, just to make sure I've understood what's happening here on the left-hand side.
Yes.
Is there an exact overlap between the blue data and the brown data?
Right.
Graph size is less than 500.
Yes, the overlap is because in this experiment, the 500 is the assumed size of the hardware. So before we hit that limit, the problem completely maps, so you don't need any software solution to stitch partial answers together. Okay, so you have a 500 node problem, and you have a 500 spin hardware. We put it on, we run it, compared to the solution of simulated annealing, you would get this speed up. And if you have a 200 node problem, you would only use part of the hardware, so the speed up is much less because the software for simulated annealing is much faster for a 200 node problem. Does that make sense?
I'm still not sure I understand why yours is identical to the D-Wave.
Oh, no, sorry. Yes. This is not D-Wave. Nothing on the left-hand side is D-Wave. The only thing that we borrowed from D-Wave is their software solver. So as our machine goes beyond, beyond the size, we took software solver.
Okay, understood. Right. I'll hand over to Viv now, whose hand has been patiently up for a while.
Hi, interesting talk. Thank you. So I joined very slightly late, so this may be stupid questions because I missed the very first slide or something. But so these are little circuits you're making, right?
Yes.
how physical size scaling is what I'm wondering about.
Okay, so that's a
right?
good question.
So how small can you make them? I mean, not overnight, right? But
yeah,
the way that CMOS has just gone down to its like whatever sub 10 nanometers that we're doing now.
Right. So for this system that we're building, the fundamental kind of bottleneck would be the ON square number of coupling units. So that's what I'm going to focus on. Everything else is ON, so they amortize and unimportant. The coupling unit, I don't have a graph over here, it requires about, let's say, 4 transistors. So it's not a very big circuit. But what we need is some degree of programming to their variable resistance. So we need a capacitor, and the capacitor has to have certain precision to that. So the current estimate, this is on 45 nanometer technology, which is not the state of the art, but also I should also say that I don't think it's an easy scaling down. We probably need the capacitor to be at certain size, so we probably don't want the capacitor to be too small. So we don't know. We now are targeting 45 nanometer. So for a 2000 node machine, this is purely from estimate, we think it's about 5 millimeter squares, okay, at 45 nanometer. And if you give us the benefit of the doubt, in a smaller technology, we just scale the chip will be smaller. But although I think there may be some limit there.
Mm-hmm. Sure. No, so so is it somewhat like an FPGA, except that the amount of configuration you put in there on these capacitors is less?
Literally, I guess we can call it a field programmable gate array. We really don't have gate. It's more like a field programmable coupler array.
Sure. But that's the nearest comparable device, is something designed to be very fast, but special purpose, but still reprogrammable to some extent.
Correct.
Yeah. Okay. Right. Yeah. I'm getting the feel for what it is. It was all great descriptions, and I'm like, I have no picture of the physical object.
we haven't fabricated the first chip, so all is just a conceptual model. The only thing that we have is, a high-level diagram.
Yeah. But you are projecting low power consumption and room temperature operation on this?
Yes. So the room temperature is for sure, and that's part of the things why we think some non-ideality, what's called PVT, process voltage and temperature variation, may come back to haunt us to some degree, although during the high temperature phase of the annealing, we're actively injecting noise, so we're not too worried about that. We believe this chip, at the current estimate, this chip of a 2000 node will burn sub-watt, so the energy efficiency should be good. And all of this is just the first design. As I already mentioned, we have a system called ZIV that we realize we don't even need later on. So I think over design iterations, these numbers should further improve. But then there are also problems that we're likely to encounter and then require us to spend some of the improvement, perhaps as countermeasures for these problems.
Awesome. Thank you very much.
Thank you.
Any other questions? If not, maybe I have one extra question, if I may. So you said this is fully classical, and it clearly is fully classical, which is fine. And there's lots of, you're exploiting CMOS and all the wonderful things that can do for you. But quantum capacitors exist. So could you imagine doing something very similar to your structure?
I totally could. In fact, we've been thinking about that. It's just our hands are full doing optimizations along this road. And if you guys have, a device model to say, this is what we can do, I'd love to take that and see what we can do with it.
Yeah, sure. I mean, of course, you lose much of the CMOS functionality. You certainly go to very low temperatures. But, I'm just wondering whether even you've thought about whether that would scale better with system size, or maybe you haven't thought about that yet.
So my this is just, zeros order guesstimate without looking in, right? So my guess, your guess is as good as mine. My worry is about coupling. Okay, the capacitors, I'm not too worried about. You can give me other capacitors, great, we'll play with them. But how do I achieve the coupling, which, first of all, it's ON, so I need a lot of them. Second of all, I need them to be reasonably accurate in coupling. And I think that may be the challenge in the quantum regime. I think that's partly why D-Wave has very few couplers per node, and that's not really solving the problem, it's avoiding the problem, right? So you really need, for an ON system, ON squared couplers, and they have to be reasonably high performance, meaning very easy to control, very stable, and all that. So that's my guess. That would be the difficult challenge if I want to go to quantum regime. The first question I would ask is, what kind of coupler you can give me, how much control I have, what's the behavior of these modules?
Yeah, that's a fair comment, I think. Yeah, good. Okay, so if there are no more questions, let's thank Michael one more time for a very interesting presentation. Thank you very much, Michael.
Thank you. Thank you. Glad to be here.
And I look forward to seeing at least some of you in Innsbruck next week at the INQA conference. And if not, the next online seminar will be in 2 weeks' time. Thank you, Michael. Bye-bye.
Thank you. Bye.